When we were discussing uniform plane waves, we talked about something called the electromagnetic polarization of a plane wave, which is basically the direction that the E field points. And then I alluded to earlier in this video that polarization can affect the efficiency of an antenna. And so let's talk a little bit about antenna polarization. And polarization of an antenna, it's the same as the polarization of an EM wave radiated by the antenna. So if the antenna were to radiate a wave, whatever direction that wave is polarized, we say that's the polarization of the antenna. In reality, the polarization of an antenna is going to vary with the direction from the center of the antenna, and different parts of the antenna pattern are going to have different polarizations. And so therefore, typically when we're referring to antenna polarization, we are talking about polarization that is in the same direction as maximum gain for the antenna. So down the center of that major lobe of the antenna, we're talking about that polarization. Because if I look, if I have my antenna lobe pattern here, we're talking about polarization in that direction, because in reality, polarization in that direction and that direction are going to be different. So we'll just kind of do an engineering approximation that polarization of an antenna is defined as in the direction of max gain. So like a plane wave, antennas can be linear polarized, they can be circularly polarized, or they can be elliptically polarized. And as you know, a linear polarized antenna, the E field vectors are always going to be oriented along the same straight line. For a circular or elliptical polarized antenna, the E field vector traces a circle or ellipse as it travels away from the source of radiation. And so what does this mean for antenna? Well, when considering the effects of polarization on an antenna, we're primarily concerned with the polarization match between two antennas. We're really interested in how does a receiving antenna align with the incident EM wave. And so this is commonly called polarization mismatch. And what polarization mismatch results in is the amount of power extracted by the receiving antenna from the incoming signal is going to be less than the maximum due to what we would call polarization loss. So how do we account for this? Well, let's assume that the E field of the incoming wave, so incoming wave, it's E field, it's a vector, it's got a magnitude of EI, and it's just got a direction of whatever its direction is. We're going to say it points in the unit vector pointing in the wave direction. So here, rho hat W is the unit vector pointing in the direction of travel of the wave. Let's also assume that the polarization of the E field and of the receiving antenna is going to be EA, and that's just EA, and it's got some sort of polarization vector for the antenna. And I can calculate the loss due to the polarization simply by calculating what's called the polarization loss factor. And that is going to be the unit vector of the wave radiating towards the antenna, dotted with the unit vector for the antenna itself, and then I square all that. So I take the dot product. In the case of linearly polarized antennas, I can make this calculation a little bit simpler, and I just take cosine of gamma sub p, and I square that. And well, what's gamma sub p? Well, it's the angle between the two unit polarization vectors. So I've got the vector for the wave, the unit vector pointed in the direction of polarization for the wave, and then the unit vector for the polarization of the antenna. And so I just take the angle between those two, take the cosine of that angle, square that value, and I get what's called the polarization loss factor. In these figures to the right here, I'm showing calculations of different polarization loss factors for different alignments of linear wire antennas. So if the the polarization vectors are aligned, the angle between them is 0. So I get the cosine of 0, which is 1, squared the polarization loss factor is 1. So what that tells you is a polarization loss factor of 1 means no loss. In the case where there's some sort of angular displacement between the polarization loss factors, I have to either take the dot product of those two vectors, or I can just take the cosine of the angle between them. And so this will be a PLF between 1 and 0 for some angle. And then finally, if the polarization vectors are normal to one another, the angle between them is 90 degrees, which means cosine of 90 is 0. So we get 0 squared, so we get 0. So total loss. So even if I have antenna that are polarized, the same exact antenna, if I align their polarizations at 90 degrees to one another, I will get total loss. So I can cause two antennas not to see one another just by rotating their plane of polarization here. So that's polarization vectors for linear antennas. What about for elliptical antennas? Well, they're a little bit more complicated, and I'm just going to limit in this class to two types of polarization vectors, and that's for right-hand circular polarized fields, and its polarization vector for the antenna is equal to a hat x minus j a hat y over radical 2. So you can see that that's an equation for a circle rotating with right-hand polarization. And then LHCP, its polarization vector is really similar. We just have a plus sign indicating the opposite direction there. So you may ask yourself, well, if I've got a linear polarized antenna and a circular polarized antenna, how do I determine the polarization loss factor? Well, I have to use the dot product here. So I take the dot product, I take the absolute value of that dot product, and I square it. If I have a RHCP and an LHCP, I have to use the dot product, right? So if a transmitting antenna has one form of linear polarization and the receiving antenna has another form, the polarization loss factor tells us that we'll have total loss. In reality, what's occurring is about 30 dB of attenuation between transmission and reception. So often we'll use the combination where we have a linear polarized transmitting antenna and we combine it with a circular polarized receiving antenna, or vice versa, and that dB loss is typically only about 3 dB. And so the combination of a linear antenna combined with a right-hand or left-hand circular polarized antenna is often used on in any sort of communication system where the angle of incidence between the two antennas changes, such as on a missile or a spacecraft or any sort of object like that.